Good morning. Can you guys on Zoom hear me?
Yep.
Okay, good. So let's get started. Yeah. So today I will just go over a brief but important point that I didn't talk about last time. And then I will discuss the falling object under the acceleration due to gravity, and then we will get to work on the activity for the rest of class time. So, continuing. Graph techniques. And then falling objects. This is the rest of section 2.8 in the book. And this is section 2.7 in the book. By the way, I skipped section 2.6, but you guys should read it because it's only problem solving techniques. Like it's an explanation of how to break a problem into parts and just problem solving techniques. So I cannot go over them in class. Okay, but you should read it. And it's not too long. So let's just do a brief review of what we covered last time. We had some graphs. We had position versus time graph. We had velocity versus time graph, and we had acceleration versus time graph. So let's start with that. This is a position versus time graph. If we have an object, something crazy like that. So what that graph means is at this point in time, for example, well, first of all, at 0 time, the object was at this position. Let's call it position, let's call it 1. And at this point in time, 1, 2, so it was here. Call this 2.5. I'm just typing arbitrary numbers. This is just an explanation of what a graph of position versus time means. It's just the position at any moment in time. Okay, so you can get the position by just dropping a vertical line from the curve and a horizontal line to get the corresponding. Okay. From a position versus time graph, we can get the velocity by getting the slope at a point, which is the tangent line. So for example, if I wanted to get the velocity at this point in time here, I will calculate the slope of this tangent line at this point. So from this graph, slope is rise over run, which is delta x over delta t. And this is the average velocity, but if it's at a point, then it's the instantaneous velocity. If I wanted it to be the average velocity, I would tell you, okay, get the velocity between point, let's say 1 and 3 time. Then you get the average. If the graph is a straight line, then the velocity is constant anyway. So assume we have a graph like this. Okay, so it's a straight line starting at x0. So if I wanted to get the velocity at t equal 2 seconds here, what you do is that you can get the slope of the whole line because the slope of a straight line doesn't change. So you can just get the initial and final points and do rise over run from here to here. Okay, so this will be your delta x, and this will be your delta t. Okay, so if I asked you to get the velocity at a point, if it's a line, you can just get the slope of the whole line. Okay, and if we have a velocity versus time graph, let's say it's doing something like this. Then each point on this graph, each point in time corresponds to a certain velocity, right? And again, if I wanted to get the acceleration, the instantaneous acceleration at a point, let's say this point in time, then we draw a tangent, and the slope of this tangent is the acceleration. So the slope of a velocity versus time graph is delta v over delta t, rise over run, and this is the acceleration. Okay. This is what we did last time. So what's new this time is that if we are given this graph and we want to calculate displacement, okay, we know how to go from position to velocity, but now we want to go from velocity to position. So we want to go the other way around. So let's write that down schematically here as from position to velocity, we calculate the slope. And from velocity to position, or displacement in that case, because it will be the difference in position between two points, we calculate the area under the curve. Calculate the area under the curve. And this is what's new for today. So for example, if I have a graph like this, let's say I have an object moving with constant velocity, or no, not constant velocity. Let's say we have an object moving with constant acceleration of 1 meter per second squared. So let's assume we have an object moving, or let's make it 5 meter per second squared. So, and it starts from initial velocity of, let's say, 3 meters per second. It's a velocity to the right. Then from the kinematic equation, we can calculate the velocity at any point in time, being v initial plus a times t, which is equal to 3 plus 5t. We can plot that on the graph here. Let's, this is 3. Then 1, 2, 3 time in seconds, velocity in meter per second. So at t equals 0, the velocity was 3. At t equal 1, the velocity is 3 plus 5, so it's 8. Something like this. Let's call this 8. And you can go on to draw the straight line. So at 2, this will correspond to 13, and so on. So now I have a velocity versus time graph. If I wanted to calculate the displacement this object made between 0 and 2 seconds. So if I asked calculate the displacement between t equals 0 and t equal 2 seconds, what I will do is I will calculate the area under this curve from 0 to 2. So this area. Starting from 0 to 2. And this area will be, so this placement here will be placement delta x is the area of the shaded region. And we can break that down into a triangle and a rectangle. So we can do the following. We can break it down, this yellow rectangle and this blue triangle. So in this case, the area will be the triangular part first, which is half base times height, plus the rectangular area, which is just length times width. Length times width. This is not color. Length times width. Okay. So here the base is just 2 seconds, and the height of the triangle is this part is the height of the triangle. So this is 10 meter per second, right? So because it's starting from 3 and ending at 13, so the height is 10. So the base is 2 and the height is 10. This is the area of the triangle, and then the area of the rectangle is the length, 2 seconds times the width, which is 3 meters per second. 2 times 3. So this is equal to 10 plus 6, which is 16 meters. So the displacement covered by this object from time equal to 0 to time equal to 2 is 16 meters. This is how you get it from a graph. To confirm that we have the right idea, let's do the exact same problem, but with kinematic equations, what we already know, to see if we will get the same 16 meters. So again, the kinematics equation are, I will write them down here. P of t equals v naught plus a t, x of t equal x naught plus v naught t plus half a t squared, 3v squared equal v naught squared plus 2a delta x. Okay. In our case, there is no. In our case, the acceleration is 5 meters per second squared, and velocity is equal to 3 meters per second. This is the initial velocity. And the initial position, we can just define it to be 0. Let's just put the origin when the motion started. Okay. So from equation 2, we want to calculate the time. We want to calculate the displacement after 2 seconds, right? So x at 2 seconds, at t equal 2 seconds, is equal to 0 plus 3 meters per second times 2 seconds plus half 5 meters per second squared times t squared, which is 2 seconds all squared, right? If you put that on a calculator, that gives you 6 meters plus 2 squared is 4 times 5 is 20 plus, so this is 10 meters, and then we get 16 meters back. And you can see that these 6 meters correspond to the area of the rectangle that was here in the bottom, the yellow rectangle. It was 6 meters, and the 10 meters correspond to the area of the triangle. So we get the same result by using the kinematic equations or by using graphical methods. So this is the important point here. If you want to calculate the velocity from position, you calculate the slope. But if you want to go back from velocity to position, placement, you calculate the area under them. Sometimes the graphical methods are easier because equations can get messy for some problems. So it's easier to draw a graph, and then if you calculate the area under the curve, you get the distance you want. This is the last problem in the homework. If I can get it swiftly. I have y is the base of the triangle 2, but the rectangle is 3. Oh, okay. So the base is still 2, but the height is 3. Let me show you the how is it working? Last problem. Thank you. Homework. Right. So last problem in the homework, you are given an idealized graph of the speed of the blood in the ascending aorta. So this is the velocity versus time graph. You are asked to calculate how far in centimeters does the blood move during 1 beat. So it's just the area under this curve that will give you the distance you want. Okay. This summarizes it for graphs. Now let's discuss falling objects. So this is not a new concept. Falling objects are objects falling under the acceleration due to gravity. And this is constant for all objects if we ignore the effect of friction or air resistance or anything. Like we're just considering gravity, okay? So independent of the mass, whether it's a feather or a heavy truck falling down, they all fall with the same rate. A equal to, well, let's say the magnitude of acceleration is 9.8 meter per second squared. All objects fall with the same rate. This acceleration is always downwards because gravity acts downwards. So if I define my coordinate system like this, let's say this is the ground, and I define the ground to be x equals 0. So this is my 0 position. And whenever I go up, actually, let's use y instead of x because it's a vertical distance, and this is pretty conventional. So this is the y-axis. So at the ground, y equal to 0. And as you go up, you get positive values for y. Okay, so for example, if you're in a 10-meter cliff, then y is 10 meters. Okay. So we define the positive to be upward. Okay. Now, if gravity is acting downwards, then the acceleration is always downwards, right? So the acceleration in this reference frame is negative 9.8 meters per second squared because it's acting downward. Okay. If I throw an object upwards, then its velocity initially will be positive. If I throw it downwards, its velocity will be negative. Okay. These are important points because science can mess up your calculations if you didn't take them into account properly. So let's actually do an example. So let's say I throw a ball upwards with a velocity of 10 meters per second. Actually, let's write it as speed. Speed equal to 10 meters per second. This is initial speed. And I want to calculate how long it takes until it reaches the maximum height and how far it goes to the maximum height. Okay, so calculate the maximum height. And the time it takes to get there. So it's always helpful to start by drawing a picture. So let's say this is the ball at the beginning. Was moving with speed 10 meters per second upwards. And this is the final position. And this is the height I want to calculate. So let's define this point to be the, let's define this point to be the origin, y equal to 0. And this point will be what we are looking for, the height we want. So y naught is 0 and y is what we are looking for. If I'm looking at the maximum height, then instantaneously the final velocity is 0. So when the ball is up top, v is 0, right? Initial velocity is positive because it's moving upwards. Acceleration is acting downwards because it's acceleration due to gravity. It's always downwards, trying to pull back the object. So I identify the knowns of the problem. And this is crucial in any problem you will do. You have to specify the knowns and the unknown you're looking for and identify the relevant equation. Okay. So the knowns here are v naught equal to positive 10 meters per second. V at the time I'm looking for, let's call it t star, is equal to 0. This is when it stops momentarily. And acceleration is negative 9.8 meter per second squared. Okay, those are the values I know. And actually, we can also put this as known. The initial position is 0. Okay. The unknowns are the maximum height, which is the position at t star and t star itself. T star is just a symbol of the time it took until it reaches the maximum height. So the relevant kinematic equation in this case, let's copy the kinematic equations and look at them individually. See how the process goes when we are solving an actual problem. So we will have the kinematics equation written here for this. Okay. So let's say we are trying to calculate the time first. Let's say we're looking for this. We are given initial velocity and final velocity and acceleration. Those three variables, and we are missing this variable. So if we look at the three equations we have, we will find an equation that connects all these four variables, which is this equation, right? Because we have on the left-hand side, v at t star is equal to 0. And on the right-hand side, we have v naught, we have acceleration, and we are missing t. So that's what we will calculate. So the relevant kinematic equation, or relevant equation, to calculate t star is equation 1. Okay. So this goes like v at t star is equal to v naught plus a times t star. So 0 is equal to 10 minus 9.8 t star. You can put this guy to the other side. So this becomes 10 equals to 9.8 t star, which means t is equal to 10 over 9.8, which is some number. .02 seconds. So this is the time it takes until the ball reaches to the maximum height. Now we want to get the maximum height itself. Since we already got the time, then we can put it to our, there are two approaches to proceed from here. So we can use the time we already calculated and use equation 2, because we will have v naught and t and a, and we will be looking for x or y in this case. Or we can calculate the third, we can use the third equation right away because it doesn't have time. So if we made a mistake when calculating the time in the previous problem, the mistake will not carry over. So we can use equation 3 more safely. Okay. So relevant equation to calculate height is equation 3. Okay, I will write it down using y instead of x because we just used y as our vertical axis. So it will be y as a function of time equal to y naught plus v naught t plus half a t squared. Just use y instead of x, it doesn't matter the variable. So that's what we are looking for. This is one thing. Oh, this is not equation 3. This is equation 2. Equation 3 is v squared equals v naught squared plus 2a delta x, or delta y in this case, because we're using y. So final velocity is 0, maximum height. Initial velocity is 10 meters per second, positive, and a is equal to negative 9.8 meter per second squared. So we can substitute that in the equation to get v 0 equal to 10 squared, which is 100, plus 2 times negative 9.8 delta y. So let me leave it as 10 squared. So this gives us, after rearranging the equation, delta y is equal to 10 squared over 2 times 9.8. And the negative sign is gone because I put it to the other side. So if you calculated that, you will get 5.1 meters. I think you already did this problem, right? You didn't? Okay. But anyway, so this is one approach. You can use equation 3, or you can use equation 2 and use the time you calculated in the previous part. But I would suggest using the third equation. So if you made a mistake in calculating the time, this mistake doesn't carry over. Okay. So that's it. Falling objects are just ordinary motion with constant velocity. It just happens that this constant acceleration, it just happens that this constant acceleration is downwards with value 9.8 meters per second squared for all objects. And then you use the exact same techniques for ordinary kinematic. Please always try to identify the givens, the unknowns, and the relevant equations, okay? Because that will make it so much easier when you're trying to imagine a problem. Also, always drawing a graph, or not a graph, drawing a sketch for the problem will help, because you can visualize it, see it in front of you, and you will get to practice that in the activity. So that's it for the overview. Now, I gave you guys the activity, and I uploaded it on Canvas as well. So the first page is just a review of the equations. I put the kinematic equations in one place, and I gave you a quick reminder on the velocity versus time and time versus position. And then questions start on the second page. Okay. You have 5 questions. Some of them are hard to solve, but they're good practice. Please ask me questions, ask Petra as well, because this way you get to learn more. And if you haven't finished yesterday's lab, you can also work on it before starting this activity. Okay. Yeah, that will be it. Get started. And if you have any questions, just let me know.